In Chapter 3, we're going to be discussing the applications of differentiation, and in 3.1, we're going to talk about our first application, which is linear approximation. We are literally going to use lines to approximate, and specifically, we're going to be using tangent lines to do those approximations. So throughout Chapter 2, we were getting questions like, come up with the tangent line equation. Well, now we're going to use the tangent line equation. The linear or tangent line approximation of f of x at x equals x naught is the function L of x, which is equal to f of x naught plus f prime of x naught times x minus x naught. That's just the linear equation. Okay? If you don't see it, that's y equals your y sub naught plus your slope times x minus x sub naught. Okay? We can then use this tangent line approximation to approximate the value of f of x sub 1. And we're going to do it by calculating L of x sub 1, as long as x sub 1 is close enough to x sub naught. So let's see what that means graphically. Here we have a curve, and that curve is f of x. Here we have a point on the curve, and we're going to create a tangent line through that point. Okay? This tangent line is L of whatever that red value is. So let's say that that red value is at x sub naught. In fact, let's make it red so we can tell that that's what we're talking about. And the y value at that point is f of x sub naught. Okay? Now this green line is L of x. But we used x sub naught to come up with L of x. So L of x is equal to that y value, f of x sub naught, plus the slope, which we know is a derivative, at x sub naught, times x minus x naught. And so if we were to plug in x sub 1 into this, which is what this is telling us to do, we would plug in x sub 1, then this x would become x sub 1. And so we get the tangent line equation of x sub 1. X sub 1 is some value over here. And so this point right here is f of x sub 1. But let's say that f of x sub naught, the red point, is really, really easy to calculate. But for some reason, the blue point is much more complicated to calculate. For instance, if I were trying to square 3, well, squaring 3 would give me 9. And that's easy. But let's say that the blue x value, x sub 1, was 3.236. Well, 3.236 is a little more complicated to find the square of. And so what this is going to allow us to do is identify a point on the green line at that same x value, and that point there is L of x sub 1, and we're going to use that value to approximate the blue value. So we'll find the pink point, and then we'll say, well, the blue point's close enough to the pink point that we can, feel comfortable saying they're about the same. Okay? And that's what linear approximation is. Now, this only works if the red and blue point are really, really close together. So you see that I have moved red and blue far apart just so we can see graphically what we're talking about here. But really, the red and blue have to be very close together to have any sort of accurate approximation. As you can see here, the further we get apart, the further we get away from red, the black curve and the green line are going to get further and further apart, and so points are not going to coincide nearly as well as when we're really close to that red point. Okay? In addition, if we let the distance between x naught and x sub 1 be delta x, so in other words, delta x is equal to x sub 1 minus x sub naught, and then delta y is the distance between these two y values, f of x sub 1 minus f of x sub naught. Then we can take this equation that we've written over here, and we can change this to delta x. In addition to this, what we're doing is we're using this linear equation to approximate f of x sub 1. So f of x sub 1 is approximately this linear equation. And then I can move this to the left side and get f of x sub 1 minus f of x sub 0 is approximately the derivative at x sub 0 times delta x. And this difference here is just our delta y. Now, we talked about it before when we were mentioning the notation for derivatives, but if delta y and delta x get infinitely small, we write it as dy and dx. dy is the differential of y, and dx is the differential of x. Up until this point, dy and dx have always been together in derivative notation. But if you separate them, they become the differentials. So dy is approximately f prime of x naught dx. Now, keep in mind that as if red and blue were infinitely close together, that means they're essentially the same point. This actually is no longer an approximation. This turns into an equal sign. So dy is actually equal to the derivative times dx. This isn't terribly important yet, but it's going to come to be more important when we get to Chapter 3. Example 1. Find the linear approximation to f of x equals the square root of x at x naught equals 16 and use it to approximate the square root of 15.95. So, we know this is a linear approximation problem for multiple reasons. The main reason is that it says find the linear approximation. Okay, but sometimes they won't say that. They'll say approximate the square root of 15.95. Well, 15.95 is really close to 16, and 16 is really easy to take the square root of. And because that's easy to take the square root of, and this one's more complicated to take the square root of, we're going to use linear approximation to do this. So firstly, f of 16 is equal to the square root of 16, which is equal to 4. This is your x value, and this is your y value. Okay? F prime of x is going to be 1/2 x to the negative 1/2, or 1 over 2 root x. F prime of 16, and again, this really only works if it's easy to calculate the function and its derivative at the value. So the square root of 16 down here becomes 4 times 2 is 8, so this whole thing becomes 1/8. And so we end up with a linear equation, and in fact, if you want to, you can write it like this. L of x, which is equal to your y value, 4, plus your slope, 1/8, times x minus your x value, 16. Now, what we want to do is we want to approximate the square root of 15.95. So square root of 15.95 is approximately L of 15.95, and that's equal to 4 plus 1/8 times 15.95 minus 16. Now 15.95 minus 16 is negative 0.05. And at this point, if you weren't comfortable doing anything else, you could leave your answer like this and get full credit, because that is an approximation of the square root of 15.95. Now, if you're okay with simplifying this and actually doing the arithmetic, this is 4 plus 1/8 times negative 1 over 20, which is 4 minus 1 over 160, which is going to be 640 minus 1, so 639 over 160. So 639 over 160 is my approximation for the square root of 15.95. Let's see how we did. So 639 over 160. Assuming, of course, I did the arithmetic correctly. Well, that's not helpful. Let's hit Control-Enter, and we get 3.99375. Well, that's really close to 4, and 4 is the square root of 16. So far, so good. Now, if we take the square root of 15.95, which we know it should be less than 4, we get 3.99375. So we were right up to 5 decimal places. Now my calculator currently is set to like float 5, so it's only showing 5 decimal places. If I change my settings for this, here, I could have clicked on the little gear up in the corner as well. Float 6. If you just hit float, and I should have made it a default, but whatever, we can go back here. And what I'm going to do now is just do this. Square root of 15.95 is not going to end that nicely. So you'll see that it keeps going. But for the most part, we were accurate up to 5 decimal places, and we did that by hand. And really, this is how, before calculators came along, they were able to actually calculate some of these weird values, like sine values, cosine values, square root values, cube root values, etc. They were able to use linear approximation to get fairly accurate. All right. Example 2, find the linear approximation to f of x equals cosine x at x sub naught equals pi over 3 and use it to approximate cosine of 1. So firstly, why are we using pi over 3? Well, it's easy to find cosine of pi over 3. That's one of our special unit circle values. It's more difficult to come up with the cosine of 1. Now, I could do the inverse cosine of 1, but those are completely different things. But pi is really close to 3, and so that would be 3 over 3, which would be 1. So that's why we're going to be using pi over 3 to approximate the value at 1. So, f of x, my color here, f of pi over 3 is the cosine of pi over 3, which is equal to 1/2. Okay? F prime of x is negative sine x. So f prime of pi over 3, also an easy value to come up with, is negative root 3 over 2. Which means our linear equation, L of x, which again is approximately f of x, is equal to our y value, 1/2, plus our slope, be minus root 3 over 2, times x minus pi over 3. Which means that f of 1, cosine 1, is approximately 1/2 minus root 3 over 2 times 1 minus pi over 3. Now this is not something that we're going to be able to simplify because we have radical 3's and we have pi's in there. But if you consider the fact that before there were calculators, people had already calculated what root 3 was and had already calculated what pi was to a certain number of decimal places. And so they were able to actually do these calculations with pencil and paper at this point. Now, we're not that advanced, so let's go ahead and use our calculator. So we have 1/2 minus root 3 over 2 times 1 minus pi over 3. There we go. So we get 0.540874. And now if I calculate the cosine of 1, I get the same thing. This one's only accurate to about 3 decimal places, kind of. They do round to something different. But 1 is not as close to pi over 3 as we would like for this particular function. The sine and cosine functions change fairly rapidly. But it's still a decent approximation. I mean, within 3 decimal places is not bad at all. Example 3, find the linear approximation to f of x equals sine x for all x close to 0. Okay, so at 0, f of 0 is 0. And f prime of x is cosine x. And f prime of 0 is cosine of 0, which is 1. So we have our slope and we have our y value. So our linear equation, so what we're saying here is that sine x for any x is approximately our linear equation, which is 0 plus 1 times x minus 0. which that simplifies to x. So if our x's are close to 0, sine x is approximately the x value. And we can see that fairly nicely if we were to graph sine x and x on the calculator. So we'll add a graph, and we'll see that sine x is that, and we'll also see that there's x. So as long as we stay close to 0, the red and the blue are almost indistinguishable. Now the further we get from 0, the more distinguishable and the more different they become. But x and sine x are fairly close together as long as we're close to 0. And we'll actually use that concept in the next section. Example 4, use a linear approximation to approximate the cube root of 8.02, the cube root of 8.07, the cube root of 8.15, and the cube root of 25.2. Okay? So the cube root of 8.02, that's close to 8, the cube root of 8, which I know how to calculate. And the same thing for this and this as well. So for these first three, I can use the same linear equation. Okay? So if I let f of x equal the cube root of x, then f of 8 is 2. F prime of x, which is going to be 1/3 x to the negative 2/3, which is 1 over 3x to the 2/3. F prime of 8 is equal to 1 over 3 times 8 to the 2/3. Well, 8 to the 1/3 is 2, squared is 4, times 3 is 12, so this is 1/12. Therefore, our linear approximation, y equals, or rather f of x equals, or approximates, the y value, 2, plus the slope, times x minus the x value. Okay? Now at this point, we can then plug in 0.02, 0.07, 0.15, and see what happens. So I am going to utilize my calculator, and I'm going to actually create that function value by calling it L of x, and I'm going to assign it 2 plus 1/12 x minus 8. That way I can see that L of x, or L of 8.02, whereas if I want to do the cube root of 8.02, fairly close. Now if we do L of 8.07, now we're getting further away from 8, so what we should see is fairly different values when we approximate and when we find the exact value, 8.07 raised to the 1/3 power. It's still fairly good. I mean, the first one was accurate to about 5 decimal places. This one's now only accurate to 4 decimal places. Now we're going to do 8.15, so L of 8.15, that's 2.0125, whereas 8.15 raised to the 1/3 power is 2.012. So this one's only accurate to 3 decimal places. And so you can start to see the further the 2 points are from one another, the less accurate it gets, but it's still fairly decent. Now if we look at this last one, the cube root of 25.2, well that's not really that close to any cubes. The closest cube is 27, but that's still 1.8 away, and right now we're trying to stay like hundredths away from the value. So let's see what happens if we use 27, because it's the only logical one that we can use. So again, f of x is the cube root of x. So f of 27 is 3. F prime of x is still 1 over 3x to the 2/3. So f prime of 27 is going to be 1 over 27. Cube root of 27 is 3, squared is 9, times 3 is 27. So now we get y equals 3 plus 1 over 27 times x minus 27. All right, so what I'm going to do now is I'm just going to plug in 25.2 into this. So 3 plus 1 over 27, 25.2 minus 27. 2.933. You'll notice I didn't store this one because I'm only doing one thing with it, so it's kind of pointless to do that. So there's my approximation of cube root of 25.2, whereas the actual value is 2.93. It's accurate to 2 decimal places, which is not great, but still, for being as far from 27 as it is, it's still doing a fairly decent job. And so you have to keep in mind that it really depends on where the numbers are, what the graphs look like, as to how far you can get away from the value before it starts to diverge significantly. Example 5. Suppose that based on market research, a company estimates that f of x 1,000 small cameras can be sold at the price x dollars, as given in the accompanying table. Estimate the number of cameras that can be sold at $7. All right. Now, this comes up every year on the AP exam. You'll notice that we don't have a $7 value in the table. So we don't have a $7 and then a corresponding f of 7 in the table. The best we can do is use these two values that are closest to 7. 7 falls between 6 and 10. So we need a point and we need a slope. Now, the point that we're going to have to use is the closest of the 2 points. Well, 7 is closest to 684. So that's the point we're going to be using for this problem, for this linear equation. Now, we also need a derivative. Well, it's going to be difficult to do a derivative if we only have discrete values. So what we have to do instead is just find the mean value, or the average rate of change, or slope of the secant line, or the difference quotient of between these 2 points, which is 60 minus 84 over 10 minus 6. So what we're basically saying is f prime of 7 is approximately, so the slope is approximately this. Now that's negative 24 over 4, so that comes out to be negative 6. And that would be in 1,000 small camera per dollar, if, that was necessary for this particular problem. It's not. We're just trying to estimate the number of cameras that can be sold at $7. So we have to build our linear equation here. So y is equal to 84 or minus 6 times x minus 6. And then we find 7, so f of 7, which we don't know. All we can do is based on what's in the table. And this is kind of an interpolation, if you want to think about it like that, in terms of some sort of statistical functionality. So f of 7 is 84 minus 6 times 7 minus 6. Well, 7 minus 6 is 1. Those are close together. 1 times 6 is 6. 84 minus 6 is 78. So according to what we have here, the best estimate we can come up with is 78,000 cameras or units. And that is example 5.